In this EzEd video lecture, we will learn what are thyristors, types of thyristors, construction and working of the silicon control rectifier, the DIAC, the TRIAC, and the Uni Junction Transistor. Thyristors are the devices having 3 or more PN junctions. The siblings of thyristor family are SCR, DIAC, TRIAC, and UJT. SCR or Silicon Control Rectifier was developed by a team of power engineers led by Robert N. Hall and commercialized by Frank W. Bill Gutzwiller in 1957. SCR is a device having structure of PNPN regions. The two structures NPN and PNP are combined together to form the PNPN structure. The symbol of the SCR is as shown. Due to the PNPN structure, we get 3 PN junctions, J1, J2 and J3 in the SCR as shown. To turn on the SCR, all 3 junctions must be forward biased. To forward bias J1 and J2 junctions, the anode voltage is kept greater than the cathode voltage, and to forward bias the junction J3, the gate is given positive voltage with respect to cathode. Consider the 2 transistor analogy for SCR. The transistor 1 is PNP and transistor 2 is NPN. The collector or the output of one transistor is connected to the base or the input of the other. This explains the interesting concept latching of SCR. Hey, it's time to concentrate now. Latching means locking. Assume a small external gate pulse is applied at the base of transistor 2. This makes the BE junction of transistor 2 forward biased and the CB junction remains reverse biased. The transistor 2 switches on and the collector current IC2 flows through it, which acts as a base current for the transistor 1. Thus transistor 1 now switches on. We get the collector current at its output as IC1. Now the collector of transistor 1 is connected to the base of transistor 2. Hence, IC1 acts as an input for transistor 2. Despite of removing the external gate pulse applied at base 2, the SCR remains locked or latched and continuously produces the output. The only way to stop the latching operation is to trigger the gate with negative pulse, which will make the BE junction of transistor to reverse bias so that it acts as an open circuit and the current flow stops. Now let's see the working of the SCR, which is divided into 3 modes as forward blocking mode, forward conducting mode and reverse blocking mode. In forward blocking mode of operation, anode is given a positive voltage, while cathode is given a negative voltage, keeping the gate at 0 potential, that is, disconnected. Thus, junction J1 and J3 are forward biased, while J2 is reversed biased, due to which only a small leakage current flows. During this mode, the SCR offers very high resistance to the flow of current and is said to be in the off state. The SCR can be brought from the blocking mode to the conduction mode in 2 ways. One is to increase the anode voltage. Beyond breakover voltage is the voltage at which the current flow starts in the SCR without the gate pulse. But this may damage the SCR. The second way is by applying the positive potential at the gate that makes the junction J2 forward biased, and being all the 3 junctions forward biased, the SCR conducts the current. Once turned on, the SCR goes into the latching mode. There are 2 ways to take the SCR out of the conduction mode. The first one is to apply the negative pulse at the gate, which will make the junction 2 reverse biased, and the SCR comes out of conduction mode. Once latched, SCR remains on till the current flowing through it remains above the threshold level, called as holding current. To bring the SCR out of the conduction mode, the current flowing through the SCR is reduced below holding current, which is the second way. In the reverse blocking mode, the negative voltage is applied at the anode and the positive voltage is applied at the cathode, which reverse biases the junctions J1 and J3, and no current passes through it. This explains the use of SCR as one-way valve, as current can only flow in one direction from anode to cathode. Consider the circuit in which SCR acts as a switch. We apply the AC signal at the input. The SCR, being one-way device, conducts only during the positive half of the input signal. When the gate voltage is applied near the end of positive half cycle, the SCR turns on and the bulb glows with the minimum intensity only till the end of positive half. As soon as the negative half starts, the bulb again goes off, as the SCR stops conducting. In the second case, we apply the gate pulse at the peak point of positive half of the input. This enables the SCR to remain on till the end of positive half, and in this case the bulb glows with more intensity than the previous case. Let's apply the gate pulse at the beginning of the input signal. In this case, SCR turns on very early and the bulb glows with the maximum intensity from the point of application of the gate trigger till the end of the positive half. Thus, we get the three different outputs for three different triggering positions. The next thyristor is the DIAC. Diode for alternating current is the diode that is used with the AC signals. The DIAC is the structure with two p-n regions connected as shown. Both the terminals of the DIAC act as the anodes, as anode 1 and anode 2.
Seriously, pay attention. This is important.
Assume the DC voltage is applied to DIAC where the anode 1 receives more voltage than the anode 2. Thus, the junction J1 becomes forward biased, but the junction 2 is reverse biased. Hence, the DIAC remains off. Every DIAC has the specific breakdown voltage. When the voltage drop across the DIAC crosses that breakdown voltage, the DIAC abruptly conducts the current due to avalanche breakdown. The DIAC remains on till the current flowing through it remains above the holding current level. As soon as the current goes below the holding current, the DIAC goes off. The same operation occurs when the anode 2 receives more voltage than anode 1. In this case, the current flows in the opposite direction, that is from the anode 2 to anode 1. Thus, the DIAC can conduct in both the halves of the input signal, acting as a two-way valve. Now, let's study the operation of the DIAC with the help of waveforms. Consider the positive half cycle first, in which the anode 1 is at a higher potential than anode 2. The two horizontal lines above the zero line represent the breakover voltage level. The DIAC switches on only when the voltage across it exceeds the breakover voltage. Thus, after the point A, the DIAC switches on as the voltage across the DIAC exceeds the breakdown voltage. The DIAC remains on till the end of this positive half cycle. Thus, till breakdown voltage, the current through the DIAC is zero, but after the breakdown voltage, the current conduction increases rapidly. As the negative half of the input starts, anode A2 attains higher potential than anode A1. Thus, as the voltage across the DIAC exceeds the breakover voltage, the DIAC conducts the current from point B till the end of the negative half cycle and the process continues. We get the same response during the negative half of the input. After the breakdown voltage, the current through the DIAC increases rapidly. The only way to bring DIAC out of the conducting mode is to reduce the current through DIAC below the holding current value, which gets the DIAC immediately off. Thus, the DIAC acts as the two-way valve, modifying the SCR functions. The next thyristor that we will study is the TRIAC. The TRIAC stands for the triode for alternating current. It's a combination of the SCR and the DIAC and has three terminals.
Hey,
It's time to concentrate now. The TRIAC is a thyristor device constructed by connecting two SCRs in anti-parallel direction. The common control terminal or the gate terminal is connected to the cathodes of both the SCRs as shown. So the TRIAC turns on only when the gate is given the triggering pulse. The basic structure of the TRIAC is as shown here. We have two P regions as P1 and P2 and four N regions as N1, N2, N3 and N4. Also, there are three terminals as main terminal 1, main terminal 2 and the gate terminal. Each of these three terminals is connected to the P as well as the N region. For example, MT2 is connected to P1 and N4, MT1 is connected to P2 and N2, and the gate is connected to P2 and N3. The TRIAC turns on only when we apply the trigger to the gate terminal. This is similar to the SCR. The TRIAC can conduct in both the directions. This two-way function of the TRIAC is similar to the DIAC. Thus we say that the TRIAC is a combination of the SCR and the DIAC. We will consider the working of the TRIAC by keeping the MT1 terminal as a reference and considering only the MT2 terminal. Thus, we get the four combinations depending on the values of MT2 and gate. For quadrant 1, MT2 and gate both are positive. For quadrant 2, MT2 is positive but the gate is negative. For quadrant 3, MT2 and gate both are negative. And for the fourth quadrant, the gate is positive and MT2 is negative. So let's see the working of TRIAC quadrant-wise. We apply the input signal to satisfy the first quadrant condition such as that MT2 and the gate both are positive. This biasing makes the two junctions P1N1 and P2N2 forward biased, whereas the junction N1P2 is blocked being in the reverse bias. A positive gate with respect to terminal MT1 forward biases the junction P2N2, and the avalanche breakdown occurs as in a normal SCR. Thus, the current follows the path P1N1, P2N2. Now let's see what happens when we apply a negative gate pulse by keeping the MT2 terminal positive. Though the path of current flow remains the same as in mode 1, but now junction P2N3 is forward biased and the current carriers injected into P2 turn on the TRIAC. Keeping the gate pulse negative, we apply the negative pulse at the MT2 also. That is, MT2 is at negative potential with respect to MT1. The path of current flow reverses and the new path is P2N1, P1N4. The two junctions P2N1 and P1N4 are forward biased, whereas junction P1N1 is blocked. The TRIAC is now said to be negatively biased. A negative gate with respect to terminal MT1 injects current carriers by forward biasing junction P2N3 and thus initiates the conduction. Let's analyze the working for the last quadrant. In this case, MT2 is kept negative, but the gate is applied positive pulse with respect to MT1. Though the path of current remains the same as mode 3, but now junction P2N2 is forward biased. Current carriers are injected and therefore the TRIAC is turned on.
Hey, it's time to concentrate now.
Let's see what output we get when we use it in the practical circuit. Similar to DIAC analysis, a positive gate trigger is applied near the end of the positive half of the input cycle, first as shown. Thus, the TRIAC turns on and the bulb glows till the end of the positive half of the input with the minimum intensity. Now when we apply the negative gate near the end of the negative half of the input, the current direction reverses and the bulb glows with the same minimum intensity till the negative cycle of the input ends. Let's apply the gate trigger at the peak of the input cycle. The TRIAC switches on immediately and conducts for the remaining cycle. Thus, the bulb glows for more duration than the previous one and with more intensity too. When the negative gate pulse is applied at the negative peak of the input cycle, only current direction reverses, but the bulb glows with the same intensity. Let's see what happens when the gate pulse is applied at the start of the input cycle. The TRIAC conducts for almost entire half and the bulb glows till the end of the positive half, that too with maximum intensity. Also, when we apply the negative gate pulse at the start of the negative half of the input, the current direction reverses, but the TRIAC conducts for the same duration as previous, and the bulb also glows with the same maximum intensity. The last thyristor which we will study is the Uni Junction Transistor. Let's see the construction of the UJT. It is a semiconductor device having only one layer of PN junction. In UJT, the silicon slice is lightly doped with the N-type semiconductor and the two contacts are taken out from this region as the base 1 and the base 2. A small P-type region is heavily doped on one side of the N region as shown. A third contact terminal is taken out from the P region as the emitter terminal. This emitter is usually located closer to the base 2 than the base 1. Hence UJT is asymmetric device. The schematic symbol of the UJT is as shown. The equivalent circuit of the UJT contains a PN junction diode at the emitter. The total resistance of the UJT is RBB equal to RB1 plus RB2. According to the voltage divider rule, the voltage drop across resistance RB1 is RB1 upon total resistance into voltage VBB. But the ratio RB1 upon RBB is called as intrinsic standoff ratio and is represented by symbol neta.
Seriously, pay attention. This is important.
Let's move forward towards the working of the UJT. Consider the UJT circuit as shown. When the input voltage VE equals 0, the diode becomes reverse biased. The total reverse bias voltage is VA plus VB, where VA equals neta into VBB and VB is the voltage across diode. The UJT turns on only when VE becomes greater than the reverse bias voltage. Hence, for VE equals 0, the UJT remains off and no emitter current flows. However, small leakage current IE0 still flows. As we increase the emitter voltage till neta into VBB, the anode voltage becomes equal to the cathode voltage. Thus, the reverse leakage current reduces to 0 and neither the forward nor the reverse current flows through the diode. The diode becomes forward biased as soon as the emitter voltage exceeds the total reverse bias voltage. This value of emitter voltage is called as the peak point voltage and is denoted by Vp. The flow of emitter current starts through the resistor RB1. This is the minimum current required to trigger the UJT and is called as peak point emitter current. Now, we know that the emitter is heavily doped with the holes and the resistance of the semiconductor material depends on the doping concentration. Thus, as the hole electron recombination takes place, the resistance decreases, leading to the decrease in the reverse bias voltage, making the diode more heavily forward biased. Thus, emitter current goes on increasing and UJT remains on. As the VA voltage decreases with the increase in the emitter current, the UJT exhibits negative resistance characteristics. The emitter terminal is given the negative trigger to make the UJT off. Based on this working, the characteristics of the UJT are plotted as emitter voltage versus emitter current as shown. Till the peak point emitter voltage, only reverse emitter current flows through the diode and hence the UJT remains off in the cutoff region. But as soon as the emitter voltage reaches the peak point value, the UJT turns on and the emitter current starts to increase. But due to the negative resistance characteristics of the UJT, the emitter voltage decreases as the emitter current increases. This region O, the graph is called as the negative resistance region. Eventually, as the valley point reaches, any further increase in emitter current, i.e., places the device in the saturation region as shown in the figure. The low cost per unit, low triggering current and negative resistance characteristics give wide variety of applications for UJT. A few include oscillators, pulse generators, sawtooth generators, triggering circuits, phase control, timing circuits, and voltage or current regulated supplies. Oscillator is a circuit used to generate oscillations. Relaxation oscillator implements the UJT as a sawtooth waveforms generator. Consider the circuit shown where the capacitor is connected to the emitter of the UJT. The capacitor starts charging and simultaneously the emitter voltage. Thus, the depletion region starts to shrink. As the capacitor voltage reaches the peak point voltage of the UJT turns on and the depletion region shrinks completely, and the current starts to flow through it. The capacitor stops charging and starts to discharge through the resistance RB1, thus generating the triangular waveform. When the capacitor voltage reduces below peak point voltage, the capacitor again starts charging, and the cycle continues producing triangular oscillations. Let's have a quick review of what we have learnt. Thyristors are semiconductor devices having 4 PN layers. The different types of thyristors are SCR, DIAC, TRIAC, UJT, etc. SCR is the thyristor having PN-PN structure. It has 3 terminals as the anode, the cathode and the gate. To turn on the SCR, the anode voltage must be greater than the cathode voltage and the positive trigger must be applied to the gate. The next thyristor is the DIAC. It has 2 anode terminals with PNP structure. The DIAC is specially used with the AC signals as it conducts in the positive as well as the negative halves of the AC signal. TRIAC is a thyristor device constructed by connecting 2 SCRs in anti-parallel manner and giving common terminal called as gate. Thus TRIAC is 5 layers PN junction device. The gate terminal controls the operation of this device. Hence TRIAC conducts in both the halves of the input, acting as a two-way switch. Uni Junction Transistor is the thyristor having single layer of PN junction. The emitter terminal acts as a PN junction diode. Thus, when the emitter voltage exceeds the reverse bias voltage of the diode, the UJT turns on and the emitter current flows exhibiting negative resistance characteristics.